let's calculate the center of mass of another object, this time a uniform isosceles triangle. I happen to have one here. Remember, this is a triangle where two of the angles are the same. So since it's more of a 3D object, we need to now define a volume density, a normal mass per unit volume. So we'll say it has density rho, and we'll say it has thickness, and we'll call that S. So if I was going to draw it here, it'll look kind of like this, the isosceles triangle, and it has a little bit of depth to it. So we can draw the back part on it like that. Like that. There we go. It's a piece of cheese, basically. Okay, now we want to find the center of mass, right? Oh, and then one more dimension is I want to give it a length. So the length is along this axis. So the way we're going to do it is, of course, we have to define a coordinate system. So I'm going to put the origin up here at the apex. We're going to go this way along the x-axis. So I'm going to call the length from the sort of this tip to the center of that base there. So that's L. So it's not along the sides L, it's the, whatever that's called, that's the L. Right? And now, what's the center of mass in terms of the x-axis? All right, so let's see, we go back to our definition of the center of mass. XCM is 1 over the total mass times the integral of each position x dm. We just got to fill all that out. So let's see, one thing we need is the total mass in terms of the parameters we've been given. Well, I don't know, I'm not real great at geometry. I was more of an algebra guy. I had Mr. Reed for geometry, he was good. But I do know, let's see, I'm going to go with the angle, the half angle there. I'm going to call that theta. And I know that this is then L, and I know that this must be L times the tangent of theta, right? Because tangent of theta is this over this, so bring that over, yeah. So this is L tangent theta. Okay, and if I want the area of this little triangle, it's 1/2 base times height. So it's 1/2 L tangent theta times L, right? But then there's two of them, so the half kind of goes away. So this area is L tangent theta times L, so L squared tangent theta, right? And then we want the volume. Well, the volume is just this area, and then it's uniform, goes back by thickness S. So the volume is SL squared tangent theta. And then the mass is just the density times the volume, so the mass is rho SL squared tangent theta. All right, so there, we just did a little geometry to get big M. So let's see, it's equal to 1 over rho times the thickness times the length squared tangent theta. And now we need to integrate. And we're going to add up all the individual pieces like this. Right, we're going to integrate along the x-axis. Each one's going to be dx wide. And it's going to have a height. Right? And the height depends on where you are in x. That's why this one's a little harder than the rod. And it's going to have a thickness that goes back s, just like the main piece. So let's see, x is just x. X is where we are. But then dm is the hard part, right? So dm, like before, dm, in this case, well, the dm is rho times dv. So we got to figure out the volume of this little slice. Let's see, so it's rho, and then the dv is going to be, well, let's see, in one dimension it's dx, it's that way is dx. That one's easy. In s, in this dimension, in the board, it's s, right? And then the hard one is the height, because the height is going to change as we go from x equals 0 to x equals L, but it's not too bad. It's a triangle. We actually talked about it. Here, this was L tangent theta. If you only made it to some region x, it's x tangent theta. Right? So that height is x tangent theta, but there's two of them. So it's 2x tangent theta. 2x tangent theta. Okay, so if that blew your mind, all this was our x. dm is rho, and this whole thing is dv. It's just the volume. Let's see, maybe this is even all correct, I don't know. Yeah, it looks pretty good. So now we see we can actually cancel a lot of stuff. Right? The position of the center of mass probably isn't going to depend on the thickness. If you change the thickness S, it would probably end up in the same place, as you can imagine, based on sort of the symmetry. So that goes away. And then the rho doesn't matter. The position of the center of mass won't change if this thing gets more dense. What else can we cancel? The tangent theta doesn't matter. That's a little weird. The angle of the triangle doesn't affect where the center of mass is. It's kind of maybe not completely expected. What else can we cancel out here? I think that's about it. So we're going to bring the 2 over the L squared. Right, and what are we going to be left with? It looks like all we have left is an x squared dx. And since we're integrating with respect to x, we have to put limits that match. We're going to go from 0 to L. 0 to L. All right. Well, that integral is 2 over L squared. And of course, the integral of x squared is 1/3 x cubed. 1/3 x cubed evaluated from 0 to L. So 2 over L squared. And then what do we got here? We're going to plug in this and get L cubed minus, and we plug in 0, we get 0. So 1/3, and that is L cubed. All right. A bunch of L's cancel. This goes away. That becomes 1, and we get 2/3 L. So one way to check your work is you better get something that is just a dimension of a length, because we're asking for a position. If you end up with L squared or L to the 5th, you've done something wrong. So this says that the center of mass of this isosceles triangle, with a little bit of depth to it to give it some mass, is always 2/3 about right here. 2/3 of L. Right? No matter what the angle it opens is, okay, I guess I can believe that. But no matter what the thickness of the density is, it's always 2/3 of L. We didn't really think about this way, right? So we could also do this whole calculation and say, as we go up and do slices up and go down, do slices down, where's the center of mass? But we know it's going to be on this axis because you can kind of use symmetry. As you move this way, it looks exactly the same on the top and the bottom on either side of this axis. And if it's distributed the same, then all the little x's times dm's are going to be the same. So we're not going to do that direction. We're going to tell you, just trust us. It's along this center axis. But along this way, it wasn't so obvious by symmetry where it was. Along this way, it's at 2/3 L. So the center mass is right there. So I can take my isosceles triangle, and I should find that the center mass is around 2/3 L, and that should be about where it balances, kind of like the rod. We can find the center mass by saying, where does it balance? Where can you balance it? It's a little hard to balance because I got to get right on the x-axis here. There we go, about right there. And yeah, that's about 2/3 L. I'm going to go ahead and mark it because now we're going to get wild here. And I've got my isosceles triangle with its center of mass. I've got my rod with its center of mass. And then we have to do it. Every physics book talks about the wrench. Where is the center mass of the wrench? It's a difficult integral to do because the shape is so weird. But we can do this trick and say, where is it? It's about right over the A where it says alloy. About right there. So I'm going to mark this one as well. And then to prove that they obey Newton's laws as a single particle, we're going to start throwing these. Hopefully nobody will come in while we're throwing the wrench. All right, first the rod that you know and love. It's got its center of mass in green. I'll throw it and spin it, and it'll move like a single object. Let's see. Not bad. Here's the isosceles triangle, center of mass in green. It's a little light, tends to fly. Let me see if I can get it to behave here. Maybe not. And then finally, here's the wrench. We got its center of mass by balancing it. It's in green, and hopefully nobody will come in here, and we'll see if this one also moves like a single object. Let me get it going here. Pretty good from here. So all of them moved, their center mass moved as though I just threw a ball.